natural disasters, climate change, overcrowding. Big problems demand even bigger solutions. It's a new era for engineering. We can build our way out of anything. To save Shanghai from overcrowding, the world's first vertical city. This is Mega Engineering.
It's going to be another beautiful day today in Extopia. A light breeze below level 200 with occasional scattered clouds between level 250 and...
20 years earlier. That is to say, today, Shanghai faces a demographic crisis. A magnet for both Chinese and foreigners, the city is becoming one of the world's most cosmopolitan urban centers. And in the last decade, 9 additional suburbs have sprung up, each the size of Atlanta.
Every time you go there, you notice more and more buildings. Literally, it's every block or every neighborhood seems to have a building going up at any given time.
But the spreading sprawl has had a devastating impact. Pollution-driven health and sanitary problems are on the rise. The city's transportation systems are overwhelmed. And it's not only a problem in Shanghai. Overcrowding in megacities is a global crisis. By 2030, Earth's population will increase by 1/3. That's almost 10 billion people. Up to 70% of them may live in cities, all demanding food, clean water, reasonable commuting times, and most of all, personal space. Meeting these needs will be a serious challenge. It's time to put an end to sprawl. Welcome to the vertical city.
In order for us to be sustainable in the future, we have to basically compact our cities. The tall building is an essential component of that.
In this future, these new structures will dwarf skyscrapers. And they won't just be destinations for commuting workers. They'll be cities in their own right. But even better, safer, more self-sufficient, more vital than their pancake counterparts, lying like fading stains on the exhausted terrain below. There'll be structures like this one. It's called Extopia. A mile high, twice the height of the tallest skyscraper, with 10 times the inhabitable interior, accommodating 250,000 people, with homes, offices, plazas, parks, even a farm, all within easy reach.
It's a place where people live, work, go to school, and go to the corner shop to buy what they need in the evening.
200,000 people would live here, with another 50,000 coming and going each day. But to build it, engineers will have to overcome daunting problems. They'll have to design an internal transportation system that can handle tens of thousands of passengers daily. They'll need a sustainable system for providing food and water for nearly 250,000 people, while making the building safe from man-made disasters like fire, as well as a direct hit from nature's deadliest storms. Believe it or not, Shanghai engineers are already experimenting with solutions to these problems. Their proving ground? A world-class skyscraper built to withstand the worst that nature can throw at it. It's called the Shanghai World Financial Center, or SWFC. At 1,614 feet, with 101 floors, this is the tallest building in mainland China, the third tallest in the world. Its innovative design, including vast open spaces which are unusual in a skyscraper, anticipates Extopia. Completed in 2008, the SWFC is a pioneer in what architects call a mixed-use structure.
In a normal situation, these structures have a mono-use. They're either office buildings, or they're residential buildings, or they're a hotel, or they're something that basically has, for the most part, a single use.
But in the Shanghai World Financial Center, shops, offices, restaurants, even a hotel are all found in the same building. In fact, the SWFC boasts the world's highest hotel, with the highest indoor pool in the world. But settling on a plan for this incredible building took an entire decade. Because the building has a flat profile, engineers struggled to design a superstructure that could withstand the high-altitude wind loads pressing on the face. They settled on a two-part solution. First, on the inside, 5-foot-wide steel reinforcements.
We used mega bracing. It's a series of these diagonal braces running up the sides of the tower, and that is able then to resist the horizontal force of the wind.
They also found a way to lighten the wind load by placing an opening at the top of the building to allow wind to pass harmlessly through the structure. It was a stroke of engineering genius. But surprisingly, it took 10 long years of cross-cultural wrangling to settle on a shape for the gap that would become the building's most distinctive architectural feature. Originally, designers planned a circular opening. It was a cultural reference to sacred Chinese moon gates, which also harmonized with another distinctive feature of the local skyline.
The Shanghai World Financial Center faces the Pearl TV Tower, which was the other landmark in Shanghai at that time. The Pearl TV Tower is organized as a series of these stacked spheres. So the original idea was for the aperture at the top of the Shanghai Financial Center to be circular. So you actually get this relationship between the solid sphere of the Pearl TV Tower and the negative circular void.
As natural as the idea seemed, it triggered a minor crisis. Because the building's owners are Japanese, and Japan was once an enemy of China.
This circle, of course, is used as a symbol on the Japanese flag.
The local government ordered a halt to construction. But then the Japanese owners made an ingenious alteration to avoid offending their Chinese hosts, trading the moon gate shape for the trapezoid. But solving cultural hiccups is easy compared to the daunting challenge of building a mile-high vertical city like Extopia. Extopia would be a jaw-dropping 3 times taller than the Shanghai World Financial Center. At a mile high, the building would need an unimposing design to avoid being an obstructive blight on the landscape. A rectangular shape that tall would create cavernous shadows below, blocking light and views. But a triangulated X is one of the strongest yet most unobtrusive shapes in architecture. Essentially an X with a tripod as a base, the form would create a relatively small footprint, providing more open space, more light, and better views. The sloping sides would provide added stability. But because of its extreme height, routine wind loads at the top would be far greater than those faced by shorter structures. And the sloped sides would also present a problem for elevators, which would have to be radically redesigned. In fact, building and living at this height will create challenges and dangers never before faced by city dwellers. If Shanghai were to construct Extopia, a mile-high vertical city, it would be the pinnacle of an age-old dream to build tall. But a vertical city would still present many of the same challenges of a traditional horizontal city. First among them, transportation. For over 100 years, the elevator has gotten the job done. But today's buildings are taller than ever, with greater numbers of people moving through them. The elevator will have to be revolutionized. 750 miles south of Shanghai, in Hong Kong, engineers are already taking the elevator to the next level. Builders are constructing what will become the 4th tallest skyscraper in the world. The 118-story ICC, or International Commerce Center. Elevator designers here face the problem of moving 30,000 people in, around, and out of the building each day. But traditional elevators present significant problems. In a building this large, elevators can actually inhibit the free flow of people. With their constant stops, elevators can force passengers to spend more time waiting than riding. That's why ICC designers set out to create an internal transportation system that goes way beyond the traditional elevator. It begins here, in the subway station at the base of the 1,600-foot tower. The subway connects to the inside of the building with 86 elevator units spread across 6 lobbies and 118 floors. Deep inside the ICC, engineers are building a single 1,600-foot shaft, one of the longest ever constructed. The first challenge for designers has been to make all the components fit into the smallest possible space. Historically, elevators have been the enemies of skyscraper owners because the shafts and the machinery eat up valuable floor space that could otherwise be rented.
We've tried to contain the actual machine rooms within the actual size of the lift shaft itself, so we don't use any other space.
They've also figured out a way to speed people to their destination floors faster without increasing the number of elevators. One innovation is to build double-decker cars that effectively double the passenger load for each ride. It's an idea elevator engineers took from bus systems. Double-decker buses more than doubled capacity without eating up additional road space. At ICC, crews assemble them right inside the elevator, one level at a time. Engineers borrowed another idea from urban mass transit. The ICC elevator system will operate like a high-speed railroad. In most buildings, an individual elevator takes its orders directly from passengers, meaning lots of stops and constant delays. Extremely inefficient. In Hong Kong, passengers tell the system where they are headed, and the system guides them to the right elevator to board. The result? More express rides.
This is a double-deck elevator system, and we are now at the lower deck. This lower deck serves all the even floors in this zone, and it recognizes its passengers, and it knows exactly which floor you're going. It's very convenient. When I flash my card here, the system will calculate exactly which lift to take me to my destination floor in the fastest manner.
When complete, it will be a super smart high-speed vertical transportation system. A first step towards the Extopian dream. But at 3 times the height of the ICC, the vertical city would require even greater innovation. A mile-high elevator shaft would use a mile of steel cable, which would present engineers with a novel problem.
Conventional steel cable on an elevator itself has a lot of weight. And so when you take this steel cable and you stretch it to 500 meters, there becomes a point where the steel cable itself becomes too heavy, it'll break under its own weight.
Solving that tricky problem will require designers to think outside the box. Literally. Traditional elevators use a rotating circular motor to lift and lower the elevator cables. But Xtopia could use lifts built with linear motors, eliminating the need for steel cables altogether.
You have to start thinking about cableless elevator systems.
Rather than creating a circular flow of energy that rotates a motor shaft, which in turn winds cable around a drum, a linear motor creates a magnetic force that pushes along a flat track. Elevators fitted with linear motors could ride an endless wave of energy, not only up and down, but along tracks laid in any direction.
Not only should elevators be able to take you vertically to different destinations, but it also should be able to take you horizontally into different destinations as well.
But even the most sophisticated transportation system in the world will be worthless unless engineers can make Xtopia safe from attack by Shanghai's worst natural enemy, the typhoon. For engineers of the world's first mile-high superstructure, one problem would tower over all others: wind.
The biggest challenge in the super tall building structurally is how you overcome the wind forces, because the wind increases proportionally the higher you go.
In coastal Shanghai, Xtopia would have to handle typhoon-force winds. Bad enough at ground level, but truly ferocious at Xtopia's nosebleed heights.
You know, you're on the ground in a typhoon, you experience severe winds, you're blown about, you've seen these images of palm trees swaying back and forth and street signs and roofs flying off of buildings. But that's at the low level, and when you go up high, the wind is even faster.
Scientists at CPP Wind Engineering in Fort Collins, Colorado, are grappling with the challenge of building skyscrapers in high winds. They are at the forefront of wind-resistant engineering, having literally written the book on the subject when the World Trade Center was built in New York City in the late 1960s. In order to determine how wind will interact with skyscrapers, engineers run models through a battery of tests. They use scaled-down foam and balsa wood models 400 times smaller than their full-size counterparts, and place them before a 20-foot fan capable of generating 60-mile-per-hour winds. The data they gather tells engineers how wind will impact the full-size structure, allowing them to adjust their designs well before construction begins. This type of analysis would be crucial for Xtopia, because the mile-high tower would be one of the first buildings to extend more than half its length above the atmospheric boundary layer. A band which stretches from ground level to approximately 1,500 feet. Winds within the atmospheric boundary layer are relatively calm, but more than 2/3 of Xtopia would be above this key layer.
Nearly all our buildings we've built in human history have been in that boundary layer. But now we're talking about buildings that are 3,000 feet or a mile high. And those sorts of extreme structures will actually be poking out the top of this boundary layer. So we haven't done much there before. It's new territory.
Leighton Cochran is CPP's lead research engineer. He says that at altitudes above the boundary layer, wind patterns are less well known and harder to predict, possibly creating more stress by striking a building face from multiple directions at once. Scientists break down wind impacts, both above and within the boundary layer, into two main types. The first is called the long wind. This is the direct airstream that hits a building head-on. But it's the second type, or crosswind, that can wreak havoc. Most buildings can easily survive a strong long wind. But combine it with an equally powerful crosswind, and the racking pressure becomes more than most buildings can take.
It's like a little baby tornado pulling the building that way because it's a negative pressure. Then one forms on this side and pulls it that way. And they have the effect of pulling the building from side to side.
Today's tall buildings are designed to sway with the wind. But too much motion can actually make people on the upper floors nauseous. So some of the world's tallest buildings are equipped with a giant counterweight called a mass damper to minimize the rolling motion. Shanghai's World Financial Center has not one, but two dampers. Hidden inside the 90th floor, they hang like the clappers in massive bells, each weighing 150 tons. The damper hangs straight down. As the wind pushes the building to the side, the angle between the pendulum and the vertical line of the building increases. The ball exerts an increasing force in the opposite direction, pulling back against the force of the wind, dampening the motion. Extopia would require dampers, but the building's shape may be the best defense against high winds. Technicians here at CPP are about to perform a profile performance test on a client's building. When air hits this flat rectangular structure, the building is visibly shaken. The test suggests that a broad, flat surface area would be a poor choice for a building as tall as Extopia. Because in Shanghai, the weather can be truly foul.
So you don't plan for your typical event, you plan for your worst case. In the case of Shanghai World Financial Center, we plan for the 100-year typhoon. What's the worst typhoon that could hit you statistically in 100 years? And that's what you plan for.
In the face of such catastrophic forces, Extopia's wide tripod base would provide critical bracing, while the complex shape of the building and the open spaces near the top would allow even the worst winds to circulate through and around the structure, diminishing the impact. Extopia's exotic shape will keep residents safe and comfortable in all conditions. And for those on the ground, it will ensure that the building will be an excellent neighbor, preserving light and open spaces below, while presenting a colorful, ever-shifting facade whose beauty is not just skin deep, but serves a vital function as well. It's a decades-old dream. A city that doesn't sprawl, but reaches for the sky. Many in Shanghai might question the environmental impact of such a megastructure. Luckily, there's a way to make Extopia both the world's tallest building and the greenest. Collecting rain for drinking water and harnessing wind and sunlight for power. To realize this remarkable promise, engineers would have to improve on traditional building materials, like steel, concrete, and most important, glass. Glass is much more than the mere skin of a skyscraper. It's a critical technology for controlling the flow of energy in and out of a structure. Inefficient glass can waste as much as 1/3 of a building's energy. Here on Long Island in New York, at a lab called Research Frontiers, engineers are perfecting the glass of tomorrow. It's called electronic glass, or e-glass. A perfectly transparent material that adapts to changes in light and heat by altering its transparency to regulate energy flow. Typically during summer months, sweltering sunlight blasts through a window, necessitating air conditioning to keep the interior of a building cool. In the winter, the opposite is true, as skyscrapers bleed heat. But if glass could be made to adapt to changing weather conditions more efficiently, buildings could save millions and be more comfortable. Steve Abadi is the head researcher at the company.
In the natural state, it's frosted, giving you privacy, allowing the light to come through but obscuring the view. When you apply an electrical field to these particles that are in the glass, the molecules line up, and that allows light to pass through and vision to pass through. Over here you see it in the frosted state, which is the natural state, and when you apply electricity, it switches to clear.
The secret is a micro-thin sheet of film sandwiched inside the glass. When electrified, particles suspended in the film realign, allowing the passage of light waves. And the glass shifts from opaque to transparent. In its darkened form, the glass limits the amount of sunlight and heat passing into the building and blocks dangerous UV rays, while providing privacy without curtains or blinds. It also uses only a trickle of electricity to control its opacity. So sheathing Extopia in electronic glass would save billions in heating and cooling costs. Extopia could adapt instantly to changing light conditions, regulating the climate inside. The amount of energy required to heat and air condition the building would drop by as much as 1/2. In fact, smart glass has such a startling impact on the bottom line, it's already being installed in some of the world's tallest buildings. Like the Willis Tower, formerly the Sears Tower, in Chicago. In Shanghai, covering the exterior of Extopia using 6-foot by 9-foot sheets would take more than 600,000 panels. The result would be a city scraper whose exterior shifts chameleon-like with changing light and weather, adding visual interest to Shanghai's already spectacular skyline.
If you're observing the building from afar, the windows will start to selectively change and darken to respond immediately as soon as the light hits them.
But if Extopia looks alive on the outside, what's even more surprising is what's growing on the inside. This is the Duo Lun Road Marketplace, one of Shanghai's few surviving outdoor food bazaars. Markets like this are an endangered species in the overcrowded city. Increasingly, fresh fruits and vegetables are hard to find. With more and more food coming from farms hundreds or thousands of miles away. In a culture where people have traditionally lived close to their food source, this is a stressful development. But Extopia could restore the balance by growing food on vertical smart farms in the heart of the mile-high megascraper. And Extopia planners could learn from seeds sown by this man. Eli Zabar is a pioneer in urban farming. His bold agricultural experiment began in 1998 when he ran into a problem. A grocery store owner in Manhattan, Eli couldn't get enough fresh produce for his East Side store during the city's freezing winter months. As it turned out, the solution was right over his head.
we had a roof that was doing nothing, and the heat rises, as we all know. The heat was just coming out of the building at the roof level and going into the atmosphere. And the original idea was to capture that heat and then try to grow things.
Today, he farms 22,000 square feet of tomatoes, strawberries, herbs, and lettuce, all on his rooftop. Eli's garden not only guarantees freshness, but it also saves on transportation expenses, costs which can make up a significant portion of grocery bills.
The average meal travels 1,500 miles from its source to your table currently. So the idea that the food can actually travel maybe 1,500 feet from the rooftop downstairs to your tabletop is really an asset.
Beyond those economies, in a temperate climate, indoor farming dramatically extends the growing season compared to outdoor farming. That means less expensive, fresher food nearly all year long. By following the lead of urban farmers like Eli Zabar, Extopia could dedicate entire floors to growing fruits and vegetables. Extopia would boast more than 100 floors, high enough to offer direct sunlight year-round. The building might even be able to produce enough to become a supplier to the city below. But to grow inside any building, much less one a mile high, growers would need nutrients. Eli solved that problem the old-fashioned way. He brought in soil and fertilizer. But despite his success, he has run up against some significant challenges. First among them, the sheer weight of soil.
The soil we have going on upstairs, when it was originally put in, was done via crane. So structurally, reinforcements have to take place. You know, it's quite a bit of volume and weight.
To add to the problem, Eli has to continually enrich the soil with fertilizer. Up to 6 tons a year. For Extopia, installing and maintaining sufficient soil so high up and in the quantities that residents would require would put too large a burden on the vertical farmers. But there may be a better way. 2,000 miles west of Eli, in an even unlikelier location, another experiment with indoor farming is underway. Hot and dry, Wilcox, Arizona, 100 miles east of Tucson, is the home of Eurofresh, one of America's largest suppliers of tomatoes. They package up to 500,000 pounds of vegetables per day here. And at 311 acres, theirs is one of the largest indoor farms in the world. And they don't use a speck of dirt. It's a technology called hydroponics, and it could be the perfect dirt-free, space-efficient solution for Extopia.
Hydroponics is growing the plant without soil and only with water. So there is an irrigation system, much like you might have in your backyard, plastic pipe, which brings the water with nutrients dissolved in that water and delivers it to each individual plant in the greenhouse.
Hydroponics is vastly more efficient than field farming.
There's as many as 10 times greater yields in a greenhouse for every square foot compared to the same square foot in the field. So you need 10 times less land.
In outdoor farming, up to 30% of water is lost to the soil. But indoor irrigation in Arizona recycles every drop. What's brought back to the plants is a precise blend of calcium, nitrogen, phosphorus, iron, and zinc, similar to the natural nutrients found in soil outdoors.
We're trying to give the plant exactly what it wants. We see what we've given the plant, we see what the plant's deficient in, and what the plant's given us back. And we change that recipe on a weekly basis to make sure that that plant's given the best recipe they could get.
And in the future, indoor gardeners like Eurofresh will have even more control over each individual plant.
As we get new sensors, we may even have the plant telling the computer when it really is thirsty and what nutrients it really needs. So we're even more water efficient and more nutrient efficient.
Hydroponic growing would be perfect for Extopia. Using smart vertical farms to feed the mile-high city with cheaper, higher quality food would also save hundreds of thousands of gallons of water annually. A critical advantage in China, whose massive population puts enormous pressure on water resources. With a plan to become the greenest building in the world, a fully inhabited mile-high city scraper could finally be the solution to Shanghai sprawl. But even as Shanghai residents breathe their first sigh of relief, engineers will have to fend off another threat before anyone moves in. They'll have to learn how to fight a potentially deadly high-rise fire. Once complete, the Extopia project would tower over Shanghai. Not only would it reduce overcrowding, sprawl, and pollution, but surprisingly, the massive Extopia megascraper would actually be safer than the smaller skyscrapers flanking it.
These super tall buildings, they're extremely well engineered just because it's such an investment to build. The super high-rise building designed to withstand earthquake and severe wind loads is a much stronger building than a shorter building, which doesn't have to experience a wind load.
As safe as it would be, some dangers would be vastly compounded by Extopia's height. And perhaps no danger is more terrifying in a high-rise than fire. Imagine it's a typical day. 250,000 residents go about their business. Children play and offices hum. When suddenly, on floor 289, a cry rings out. Waves of heat and smoke pour from a nearby theater. A short circuit has led to a fire growing quickly in intensity. Patrons flee and an alarm sounds. If the fire spreads, hundreds of thousands could be in danger. Fortunately for residents of Extopia, advances in steel technology and structural design have virtually eliminated the possibility of a total structural failure. But containing a raging fire in the heart of a 300-story skyscraper would still be a daunting challenge. Firefighters could apply tactics developed by experts in high-altitude firefighting here in Chicago, Illinois, home of the Sears, now Willis Tower, the John Hancock Building, and the new Trump Tower. Chicago has been and remains the cutting edge of high-rise living, and firefighters here have perfected the dangerous science of fighting sky-high blazes. These rookies are beginning a strenuous 6-week training course. Their instructors say these are the most crucial weeks of a firefighter's training, because perfecting the skills they learn here could mean the difference between life and death should they ever be called on to fight a high-rise fire. Skyscraper firefighting teams must attack their fires in a carefully choreographed way. First, a fire investigation team moves in to scout the fire and lay out a plan of attack. This team pinpoints the fire's location, analyzes its severity, calculates its likely path. Then the incident commander sends in attack teams made up of 3 to 5 firefighters to hit the fire from multiple angles, driving the inferno back and hopefully smothering the flames altogether. Firefighters battling a conflagration in Extopia would use the same multi-pronged strategy. But these battle-tested tactics could potentially be complicated by the building's extraordinary height.
One of the big challenges for high-rise is manpower. Anything past the 8th or 10th floor, depending on the setback of the building, how far it is from the street, We can't use ground ladders. We can't use our aerial ladders. So everything's got to go up either by the stairway or by the elevator.
Extopia could counter the need for cumbersome movement up stairways and elevators by spreading local firefighting units throughout the structure, just as in a horizontal city. Safety engineers try to plan for every scenario. In the event of a fire on Extopia's upper floors, a ventilation system could draw oxygen away from the flames, helping early responders get the blaze under control quickly. But there's no guarantee that the fire wouldn't find another source of oxygen. A broken window, perhaps, leading it to flare up again even stronger. In that case, fire teams from other stations in the building would heed a call to marshal their forces. In all likelihood, they would be able to contain the inferno. But in the rare case that the fire continues to grow worse, the fire commander would be empowered to make the ultimate call: evacuate. But herding 250,000 residents down 300 stories of stairs would take hours. And even if it could be done, it wouldn't be safe.
You really wouldn't use your elevator because there's always the danger of your elevator shaft becoming a chimney. The smoke is going to go right up through the elevator shaft.
Instead, high-rise architects have proposed a bold, counterintuitive strategy. Endangered residents could evacuate without leaving the building at all. It's an idea put into practice at the Shanghai World Financial Center. Engineers here have constructed safety zones called refuge floors. One every 12 stories.
What we need to begin to do is think about if there's a fire in the building somewhere, how other parts of the building provide safe havens for people while that fire is being fought. There are areas of refuge that are designed so that everybody comes to that floor, and if need be, the firemen can come to that floor to evacuate people.
On the 289th floor, as firefighters battle to bring the fire above under control, nearby citizens would evacuate into Extopia's safety floors, waiting for the all clear. If realized, Extopia would be a glimmering icon in Shanghai's growing skyline. An alternative path to address the problems of sprawl, overpopulation, and unsustainable growth. It would certainly forever alter the human experience of the city.
I think the skyline in the future will change. They'll be dynamic, they'll be exciting, they have to lift the spirit, and they have to be places where you can immediately understand, yes, I want to be there. I want to be part of that community.
For Shanghai, Extopia would be a radical leap forward and an engineering triumph to rise over all others.